Hi, I'm Kathy Levinger. In this lesson, we're going to look at the rate of change and slope of a line. Let's start with the definition of rate of change. The rate of change of one quantity A with respect to another quantity B is the ratio of the change in A to the change in B, written as change in A over change in B, written in fraction form. For linear functions, the rate of change is constant. Well, let's look at an example. Here we want to determine whether the function shown in the table is linear. If it is a linear function, find the rate of change including units. Well, a function is linear if its rate of change is constant. To figure out the rate of change, we'll consider the top row of the table to be what's called an independent variable and the second row a dependent variable. And we'll find the step to get from 0 to 2.1, that's 2.1. To get from 2.1 to 4.2, we go 2.1 units. To get from 4.2 to 6.3, we go 2.1 units. And to get from 6.3 to 8.4, we go 2.1 units. So there are equal steps in the independent variable. Now we have to figure out the steps in the dependent variable, and the first one's 7.98. We can see from 0 to 7.98. We need this step, which is found by taking 15.96 and subtracting. So let me indicate what we can do is do 15.96 and subtract 7.98. And you'll find out, or you'll find that that step is 7.98 also. If you do that subtraction again, you get a step of 7.98 here and here. So this is a linear function. It's a linear function because equal steps in the independent variable produce equal steps, 7.98, in the dependent variable. To find the rate of change, what we're going to do is put the step in the dependent variable over the step size in the independent variable, and then divide with the help of a calculator. We'll do 7.98 divided by 2.1 on a calculator. 7.98 divided by 2.1, and I'll let you see how that calculation looks. That result is 3.8, and we'll write that down as our rate of change. Let's continue by looking at another definition, or actually another name for rate of change. Another name for a rate of change is slope. By definition, we say the slope of a line is the ratio of the change in the dependent variable, the vertical change, to the change in the independent variable, which is the horizontal change. Kind of shortening the definition, we can say the slope is equal to the vertical change over the horizontal change for the line. Vertical over horizontal. Well, let's use that to do the following. We want to use the graph of a linear function shown to find the rate of change including units. We're going to use the fact that the slope, or rate of change, is the vertical change over the horizontal change. And let's pick a couple of points that are convenient to use on our line. Let's say these 2 points. This point looks like it corresponds to 0.10 and then 3.30. But really what I want to do as I write down the rate of change is just note the vertical change from this point to the next is up 20. The horizontal change is to the right 3. And so that's the rate of change, but we need to attach units. The units on the 20 are miles. The units on the 3 are hours. And so we could say that this rate of change is 20 over 3 miles per hour, attaching units. Let's try another example. The table below represents a linear function. We're told it's linear this time. We want to find the slope of the graph of the function. Well, the slope, just like the rate of change, is the change in the dependent variable divided by the change in the independent variable. So let's pick a pair of independent variables, 3 to 5, and I see the change there is plus 2 if I go from 3 to 5. Let's take their dependent variables. To go from 1.08 to 1.80, I must go positive 0.72. So the change in the dependent variable over the change in the independent variable will be the slope of the graph. We'll say it's 0.72 and attach units, dollars per 2 pounds. We shouldn't leave a decimal in a fraction, so let's divide that using a calculator. We'll do 0.72 divided by 2. The end result of that is 0.36. So we'll say our slope is 0.36, and I'm going to put a $sign per pound, $0.36 per pound. Well, let's continue by looking at another example. Again, we want to use a graph to find a slope of a line, remembering that the slope is the vertical change over the horizontal change. And let's look at some convenient points on our line. I see that this point corresponds to 5 on the y-axis, it's labeled y, and that point corresponds to 6 on the x-axis. To get from the point at the left to the point at the right, I need to go down 5 to the right 6. Down 5 is indicated with a negative sign, to the right 6 is positive, and so negative 5 over 6 is the slope of that line. Well, let's continue by looking at a definition that'll tell us how to get a slope if we're given an equation of a line. Here's that definition. For a linear function in the form f of x equals ax plus b, or y equals ax plus b, the slope of the line is a, which is the coefficient of the independent variable. So again, the slope of the line is the coefficient of the independent variable once the dependent variable sits by itself on the left-hand side, either y or f of x. Let's try this out. For these examples, we want to find the slopes of the lines represented by each of the following equations. The first equation is f of x equals negative 3x minus 2. This is already in exactly the form in the definition, so the slope, which is represented by the letter a, is negative 3, the coefficient of the independent variable. In our second example, we have the equation 4p plus 3q equals 1. And we're told q is the dependent variable. In order to get the slope, we need to isolate q, or get q by itself on one side. To do that, as a first step, I'll subtract 4p from each side of the equation and write 3q equals negative 4p plus 1. To get q by itself from here, I need to divide by 3, and I'll divide each part of the equation by 3 to get q equals negative 4/3 p plus 1/3. Now that the dependent variable has been solved for, the coefficient of the independent variable is the slope. So the slope, a, is negative 4/3. In our third equation, we have 6y minus 4x equals 3x plus 5, and we're told y is the dependent variable. We need to get y by itself in order to identify the slope.